Okay, so the next process, and I'm moving over to page 309. So technically, again, if we were doing these problems, which you're not writing them down. I'm just using it as my teaching guide. This is really weird to teach this way, by the way. It feels super awkward. Because at this point, I would want to be looking at your faces and seeing who has questions and checking on you guys, but I have no idea where you're at right now. So pause, rewatch, all that, send me questions, blah, blah, blah. Same old, same old. Okay, so before number 3, it gives you this example of branched polymers. So branched is like when you have a straight chain, but then off of one of these, you have a whole nother chain stemming off of that. And maybe off of this one also it kind of branches off. And so I tried to color code that image here like that. And so the yellow would be that main chain, kind of the main original longest chain that we would use to name this polymer. And then the red are 2 different branches. So you can see off of here, there's a branch coming. Wow, I can't go backwards. And then there's another branch over here coming off that way. And so those branches, if you can imagine, totally mess with the slipperiness of the polymer. So are they going to slide as easily? The properties are going to be different. If you just have nice, long, straight chains, then they can all kind of slip past each other. Well, if you have these branches, it's going to make that polymer more rough and chunky, and that shifts the properties of the plastic. And so number 3 says to just draw some random models using our simplified string versions of some branched polymers. And so here's my example of what that might look like. Okay. There's the branches kind of stemmed off, a couple different examples. Maybe we have one really long chain with tiny little branches versus, some long chains, but with also long branches stemming off of it. So those are just some ways that we could have some branched polymers. And that's number 3. And then 309 goes on to just really say like, hey, it's going to change the properties of it. And so it says what molecules would have the higher boiling point? Like, how's that going to affect when these things melt, when these things boil? And so really, for that number 4 question, the ones with shorter branches, so like this one right here, the ones with shorter branches are closer together. So when they're closer together, guess what? They have more intermolecular forces. You remember that from like when we did real school? So when they're closer, like if here's one polymer and here's another one, maybe. Hey, look at that maroon and gold. If they're closer together, like the branches aren't holding them away, then they can interact more and they have more dispersion forces. So smaller branches are going to hold those molecules in together. They're closer. Their electrons and whatnot can interact more versus these longer branches over here. That's going to make a lower boiling point. It's going to boil a lot easier at a much lower temperature because they're already spread apart anyway. And remember, the part of boiling is to separate the molecules. So if these guys are in tighter, close quarters, it's going to be harder for them to separate. We need more energy, higher boiling point, versus these bigger branches over here, further away already, because, if you think of a big tree with big branches, it's not going to be as dense. And so lower boiling point because they're already kind of separated and they can't interact as much as these guys. Okay. So that's kind of that as far as branched. And then my last little segment is going to stem on cross-linking, which is my favorite. I love cross-linking, and this slime article hints on it. I don't know if you know this, but slime is popular in my house. And so we, the Carter family, really appreciate the cross-link. So hang tight for the last little piece on this tutorial.